Top of the morning to you.
Hello, laddie.
Aye. We're going to hit you up with our unit vocab for moles and Stoich.
Yeah. Words you got to learn.
Deuce. Oh. Yep. Define and specialized vocab of moles and Stoich.
I'm going to preface this with this. Ready? This unit is much more cut and dry than the last unit.
Mm-hmm.
Last unit had some definitions, man, that were mad close for like 3 words, same definition. Not this unit.
Yep. So let's hit them up.
Do it.
First things first is the mole. Okay, there is a great graphic for how we chemists relate mass, volume, particles of a mole. But it is used typically as a standard scientific unit for measuring large quantities or very small quantities of compounds or elements and atoms and molecules. We use this to count.
Yeah. I really can't resist the urge. Ready? I say a dozen, you say
12.
And I say a mole, you say
6.02 times 10 to the 23rd particles.
Boom, and there's the number. And that leads us to the next. That is Avogadro's number. So this is a very specific number. This is how many of anything are in a mole. Right. You can have a mole of envelopes. You got that many. Mm-hmm. Okay? It's just a number. It's just a huge number, so don't freak out.
Astronomical.
So this is the number of these elementary particles. We're going to say molecules or atoms per mole. And that's the number, 6.02 times 10 to the 23rd.
1 mole equals 6.02 times 10 to the 23rd.
Equals.
Mm-hmm. Sweet. I almost wanted to put it as an equation, but hey, you can write it in your margins.
There you go. Next.
Gram formula mass. Okay, this is a way that we chemists relate the number of atoms in a molecule to how much that molecule would weigh if we had a mole of it. So it's the total mass of each atom in a molecule in grams, but that altogether as grams represent 1 mole of that substance. So
this is how we can use mass
to measure and count. Yeah, right. If I need 1 mole of water, I do the gram formula mass for H2O. I find out it's 18. So now that I know that's 18 grams per mole, I can put 18 grams of water on a scale and say, I got 6.02 times 10 to the 23rd molecules of water in my hand.
And it's much easier to say, I have 1 mole, right?
Than that, right.
So don't get all upset about the mole. All right, mole coefficients. And see the numbers in front. Coefficients in red. Coefficients come first, just like in math. So this we're not going to deviate from this unit at all. This is the number in front of the product or the reactant tells us how many moles. Call that the mole coefficient.
How many units of each molecule are in that equation?
Yeah, you on blue.
I am on the subscript. Subscripts are telling us how many atoms of each of that type within the molecule are present. So H2O means there's 2 H's and 1 O in a water molecule.
Correct.
And the subscripts are what is telling us that.
Right.
If there is no subscript, we assume there's a number 1 there.
Correct. And then this gets back to counting. We need to be able to count right every time to get this whole unit right. Limiting reactant. The picture's trying to show you I got 4 hot dog buns, but I have 5 hot dogs. So how many can I make? I can only make 4. I run out of the buns. They are what's called my limiting reactant. Right. So this is just the thing I run out of first in my chemical reaction. When I run out, the reaction stops. Hey, you know what you're going to do.
That's right. The law of conservation of mass. There's a couple ways to think about it. If you count the atoms or if you actually count the mass, it basically means that in any kind of chemical process, matter cannot be created or destroyed. So nothing can actually go missing. It can only be rearranged into new or different things. And we as chemists go to great extents when we do moles and stoichiometry in a chemical lab to make sure that we didn't lose anything. Or if it's not here, where did it go? What happened? Because we can't see the atoms. We can't see the molecules. We have only to look at a scale.
The tough part is the gas. If it turns into a gas, it's tough to keep that stuff. Balanced chemical equation. So here is one. It is balanced. Look, I have the same number of irons and oxygens and carbons on both the sides. And so this is following that law of conservation of mass, expressing whole number ratios of reactants and products. Reactants happen. They react to form products. And I think that we can come to an agreement that products are the final thing. It's a product.
You always produce it. A synthesis reaction is whenever you take 2 species, compounds or elements or whatever, and put them together to make 1 product. So usually a really quick and simple, dirty way to think about it is like 2 reactants, 1 product.
Facts.
2 or more things come together to make less things.
Yes.
They're coming together, synthesizing.
Yes. Decomposition is exactly the opposite. This is breaking apart 1 thing into 2 things. So it's backwards, right? This is a reaction that makes 2 products from 1 reactant.
Right.
Or how about we can say more products from less reactants? So it's fine too.
Breaking it down.
breaking it down.
A single replacement reaction is simple. It usually involves just one element, pure, swapping in to become an ion within the compound. It like kind of kicks something out and says, hey, get out of my seat. I'm sitting as. And so it's a reaction. It switches one element out of a compound for another.
Yep. And then a double replacement happens twice. So instead of just having an atom and a compound, now I have two compounds and a species from either compound switch, as you can see.
Yep.
So I have a double replacement. Two different atoms are being replaced, one in each compound.
Mm-hmm. A molecular formula is simply the formula of how a molecule would be in the real world. So CH4 has one carbon and four hydrogens. That's a molecular formula. H2O, two hydrogens, one oxygen. That's a molecular formula.
Sure. And some of these molecular formulas that are large can be broken down into what we call the empirical formula. So you can see on the left-hand side, I got molecular formulas, and then just a reduced form into those simplest terms is what we call the empirical formula. They're like the building blocks. Mm-hmm. So this is just a reduced formula of any real-world molecule in its like base units.
Yes, it's abbreviated. It's an abbreviated real-world molecule. Yeah. Percent by mass, percent composition is exercise that we do to figure out how much of each portion of a compound is due to the mass of this or that element. So it's a ratio of an element's mass to the mass of the whole molecule or compound. Sure. We do them in percentages. So it'll say H2O molecule is this much percent by mass H and this much percent by mass O. When you take all those percents and add them up together, you should get back to 100%.
Facts. Mm-hmm. Facts. Products. Ooh, this is a good one. We need to get this right.
Burn it
whatever,
into your
for
head.
whatever reason.
Get a tattoo. Problems. I should get another tattoo. Reactants and products.
One on one arm, one on the other.
Yeah. Got to have an arrow. That'll be added to my chemistry tattoo.
Nice. Anyways, you see that the products here are on specifically the right-hand side of the arrow.
Oh my God.
Whatever you come up with to remember that, my God, you cannot get it wrong. You need to be able to tell me that. So this is the elements or the compounds as the result of a reaction, always found on, again, the right side of the arrow.
Wherever the arrow is pointing is telling you what you made.
Yeah.
So you produced that. The reactants are what was used to make the product. So it was on the left side of the arrow, the tail end of the arrow, the elements and compounds that start the reaction. It's found usually to the left-hand side or the tail end of the arrow.
I like to think the reactants react to form products.
That's literally how it works.
Literally.
Yes.
Polyatomic ion, we've been seeing this a bunch. This is a thing that we got to not get away from because we are slowly becoming fluent
with them,
right? Yep. And it's taking some time, but that's okay. This is a group of atoms forming a single ion by definition. We got a table E to help us with them.
Mm-hmm. Hydrates are an entire class of a compound. They have their own special notation. They have this chemical formula like BaCl2 and then dot 2H2O. It means that there's water molecules attached into the other part. So all four of these are technically considered hydrates. There's a dot and then some amount of H2O molecules in it. Yeah. Hydration means water. And when you are hydrated, you've added water into yourself. So you've infused water into these compounds. So we call them as a class hydrates.
Yes. And we're going to deal with percent compositions with those. And we're going to deal with, what's the other piece? Gram formula mass.
Yes.
And that how we do gram formula mass with that dot. Pay careful attention. Let's not get screwed up. Parentheses specifically is when we have more than one polyatomic ion. So you've seen these polyatomic ions before, and I only have one NH4. I don't necessarily need a parentheses. But when I have three of them, I need a parentheses to say that there are three of them. So that's what the parentheses really means. It's like cubed in math class. Okay? Yeah. There's three of them, and then there's one PO4. So what he did was kind of break it out longhand, and let's be honest, that's doing too much. We can just put a parentheses with a 3, and it means the exact same thing. What you need to do, and it's NH4, by the way, not NH3, but that's okay.
My bad.
What we want to make sure we do, though, now is this comes into play when we have to count the number of atoms. We need to not mess that piece up. So this is just the notation used in a formula that denotes multiple polyatomic ions, and I believe that's
it. It's true. Memorize. And I should memorize where the button is. Push the button and turn it off.